Hope you are doing well. Today we are diving into the exciting topic, which are some good functions that you can use, and in this we'll see today the world of polygenetic tree constructions and analysis. We have already laid the foundation of our previous video exploring the basics of Biopython and bioinformatics. Now it's time to take our understanding to the next level. When I say we are here to take our understanding to the next lecture, in the today's lecture we'll be using Biopython, powerful library, you all know about it of course, for computational biology to decipher the evolutionary relationship between the species. So this phylogenetic trees are our map guiding us through intricate web of life, showcasing how species have evolved and diversified over millions of years. Remember what I'm saying? Millions of years. Maybe not millions, billions of years. But before we embark on this journey, let's recap what the thing we have learned so far. The Biopython, as many of you know, is a versatile toolkit that simplifies complex biological data analysis. It allows us to manipulate and explore DNA, RNA, protein sequence with very ease. Not only limited to DNA, RNA, protein sequence with ease, but also some extremely difficult topics of biology that we generally fail to do so. In our previous video, we also covered the basics of Biopython, in which we came to know how to read and write sequences, access sequence informations, and perform simple analysis. So this is what we have already done in our previous videos. But today we are going to apply those skills to construct and interpret the phylogenetic trees. Yes. Now brace yourself for some fantastic bioinformatics. We'll start by importing our trusty Biopython module, then read sequence from various species. We'll give them meaningful IDs for clarity and create multiple sequence alignment to compare their similarity. After this, next we'll calculate a distance metric. Don't get confused and overwhelmed by listening to this word matrix. It's going to be very simple. A virtual tool for measuring the genetic differences between our species. The matrix will serve as the foundation. Remember, it will serve as a foundation of our phylogenetic trees. Now let's be some analytical. With our distance matrix in hand, we'll construct our first tree using UPGMA algorithm. Don't get confused and don't get overwhelmed by this terms, matrices, UPGMA algorithm and all. It's simple. The tree will represent the hierarchical relationship between the species based on their genetic similarity. Now let's get some eagerness. We won't stop there. We'll explore our trees, find common ancestors, and discover just how interconnected the tree of life truly is. Then we'll briefly touch on the neighbor joining algorithm. Don't worry, I'll be explaining this all things in very detail. By the end of this lecture, you'll have a solid understanding of how to construct, visualize, and analyze. Remember, construct, visualize, and analyze phylogenetic trees using Biopython. So let's embark on this scientific adventure together. So are you ready? Fantastic. Let's begin our journey into the intricate world of phylogenetics and Biopython. Please pardon me if I'm pronouncing any of the words wrongly, because technically I'm not a biologist, or technically I haven't read much of bio in my life. I'm just a computer scientist who is trying to include his codes in some biological format. So please pardon me if I'm pronouncing any biological terminologies in a different way or in a wrong way. So my apologies in advance for that. Strap in, folks. It's going to be a fantastic ride. So first of all, let's begin to a Python code, and do not worry, whatever Python we have already discussed till now, whatever Python codes right now I'm discussing, you can already see this into the screen with me, or sometimes but in front of me. With this Python codes, will also be providing this Python codes to all of you, so you can also plug the same Python code in your Anaconda library, and you could input it into your Jupyter notebooks. You could run it by yourself and you could see it We have already discussed some of the basic nitty-gritties and some of the basics of how to open the Jupyter notebook and Anaconda and things like that in our previous video. If you don't remember it till now, and if you haven't done it till now, please go back and do that thing firstly. So that is one of the basic important things. This all codes will be provided to you. You will have this code and you can run this codes. Remember, a shortcut for running a code in Python tab is shift and enter. The moment you write shift and enter, you can run a code. Now we'll just discuss this Python code that we have in front of us. We'll start with importing necessary libraries for this. First of all, we have to import bio as bio. Why? Remember, this initial bio should start with capital B. If you're writing it as small b, it won't work. Second, from bio, a module named as bio, we are going to import a specific functions which is sequio, which can be elaborated at sequence, input and output. Remember, S should be capital in sequio. S should be capital, I should be capital, O should be capital. Again, if you are writing it into the small form, it won't work. Next line, we are having from bio, import align IO, align input and output. A should be in capital. After that, we have import Phylo, Phylo, P should be in the capital. I'll be explaining each of them one by one, what functions they are containing and how we are using them in different scenarios. In this section, the code imports the required Biopython module. It's worth noting that the bio package is imported twice, which is redundant. You only need to import it once. Any which ways, the next code you can see is we are trying to read the sequences. The sequences has FASTA files, that is FASTA files. Like we have files in CSV, like we have files in Excel and PPTs. Similarly, we have a different kind of file which is known as FASTA. First thing what we are doing is we are creating a variable named as P1, which equals to sequence input type output. It will read any FASTA file, For example, I have written it boss underscore TAURAS dot FASTA file because that was one file that I was having. You can read any of the FASTA files that you want to deal with. Remember, if you want, we can also provide this particular file to you, but it's always good to have your own FASTA files. Just search it from the net. You as a biologist, you know which FASTA files are more linked to you, and you can work on that particular thing. It would be better always. We have P2, which again we are reading it by writing sequio canis underscore lupus dot FASTA file, again another FASTA file. After that, P3 to P12, we are trying to read sequence from other files. So here the code, what this code is trying to do, this code reads DNA, first thing, DNA or protein sequences from FASTA file. So you are having a FASTA file, it is trying to read either DNA or the protein sequence and then assign them to the variables from P1 through P12. So P1, P2, P3, P4, P5, P6 and so on till P12. After this, we have code which is assigning IDs to sequences for better understanding of the tree. And what these IDs are, P1.id is equal to bovine, P2.id is equal to dog. So first ID is assigned to bovine, second ID is assigned to dog. Similarly, P3 to P12, we are assigning ID to other sequences. This script assigns human readable identifiers, that is IDs, to each sequence. This IDs will be used to label the branches of the phylogenetic tree for better interpretation. Now, the upcoming code is, in this particular code, we are reading the alignment. Remember the file that we have imported, a file which was align.io, and I told you that I promise you that on some stage I'm going to tell the uses of that align.io. Here's the use of align.io. It is reading an alignment from clusteral W format file and with open align.clw and quoted R. It should read, that is why we are writing R as CLW, in which alignment is equal to align.io.read. We have imported it, align.io. Now we are reading this CLW file as clusteral. Don't get confused. These all things are just very simple. The moment you try and utilize it and try and write it down in your Python notebook, you run it by yourself, it all will become very crystal clear, and you will see the magic of codes the moment you try applying this all codes. This sections opens and reads an alignment file in the clustral w format, align.clw, and stores it in the alignment variable. And alignment is a way of rearranging sequence to identify regions of similarity, which is essential for phylogenetic analysis. We are just trying to rearrange the sequences to identify regions of similarity. So this we have realigned it, and we are trying to find this is similar to this, this is similar to this is similar to this. I hope you understood this. Next code of our Python talks about calculating a distance matrix based on identity, in which the code starts from bio.philo. We have imported the philo before this, remember? Yes. Philo.tree construction, we are importing distance calculator. So actually I'll be very frank with you all, this all formulas and this all predefined libraries that we are using, to be very frank, to just check this distance calculator and all, you actually need to do some maths. If you don't do, or if you don't use this particular functions, you might need to use certain big numpy libraries, and you have to write the mathematical expressions by yourself. I don't think you want to do that. That is why we have a distance calculator as function. So this distance calculator in the brackets, it's a function which takes identity inside it, and it kind of calculate the distance between. Again, we have a distance matrix that has calculator.getDistance, and it takes the alignment. So what we are judging here, we are just trying to judge the different distances from each point, and we are trying to create a matrix. How cool is this? Remember, if you want to do it mathematically, if you want to do it by yourself, you have to read all the way from linear algebra, and you have to read all the sorts of math and the matrix calculation and everything, including matrix inverse at certain times, which might be painful for you all. But this complete function makes it too much easy, so that you could just import it, you could just use it, and the matrix is in front of you. The code calculates a distance matrix based on the identity model. This matrix quantifies the genetic distances between pairs of sequences in the alignment. The distances are printed to the console. The output appears to be a triangular matrix, remember, not a square. It appears to be a triangular matrix where rows and columns represent sequence, rows and columns represent sequence, and values represent the genetic distance between them. So here we are trying to construct things. So from here our construction is kind of starting. The next code is something which specifically talks about constructing a phylogenetic tree using UPGMA algorithm. Don't get confused and don't get overwhelmed. From bio.philo.tree construction, now we are trying to import. Remember, whenever we are seeing this very dangerous stuffs in your terms, whenever we are seeing very complex stuff, don't get overwhelmed. Just try to write it down without getting very nervous about seeing these codes. Just try to write down these codes in your Jupyter notebook. Just try to run it. Sometimes try to manipulate it, just edit certain parts of it. Okay, if we do this thing in this, if we just import this thing in this, if we just change this particular thing in this, you will see and you will understand how this codes actually work. So what we are doing here is this tree construction using UPGMA algorithm. We are, first of all, we are just trying to import bio.philo.tree construction. From this we are importing distance tree calculator, in which we are saying constructor is equal to distance tree constructor. And whenever we are saying distance tree constructor, we are just calling this particular function. Just come function, come calculate this distance for me. After this we are saying UPGMA tree equals to constructor.upgma distance matrix. This UPGMA is nothing but an tensor algorithm, I'll tell you. And from here we are just trying to create this particular matrix. This part of the code nothing is doing nothing but it construct a phylogenetic tree using UPGMA. I'll tell you the full form also. Unweighted pair group method. Unweighted. It's not having any weights. Unweighted. It's not having any weight. Pair. It's in pairs. Group methods. We are kind of pairing and creating groups. I'll repeat it for you. Unweighted. It is not having any weights. Unweighted. Pairs. It is having certain pairs. Group method. We are kind of grouping it with arithmetic mean. Whenever I'm saying arithmetic mean, that does mean particular total values mean. You all have somewhere or else read basic mathematics in class 10th at least. We all know what mean is. The tree is stored in the UPGMAT or UPGMA tree variable. The next Python code that we are right now dealing with is we are creating matplotlib. I'll hold you for a second here. Matplotlib. It is a very useful tool. This matplotlib is a very useful tool for the visualizations, any kind of visualization for that matter. Not only in the biology but also in the world of maybe if you want to do something else tomorrow, includes visualization. This matplotlib library is going to be your favorite companion, and this particular function is going to save you lot from creating some different kind of visual tools that you have to create while by using some complex mathematical formulas. It makes you easier for you. Just you need to plug in certain function, it will create a good visualization for you that will amaze you the moment you see that particular visualization. Now the first thing that we are looking at is the figure, in which we are writing fig equals to plt. It is plt is nothing but plot. Plt dot figure, in which we are deciding what should be our figure size. The figure size is 20,12. That does mean I want 20,12. This is my area. You draw it in my area. 20,12. DPI is equal to 300. Okay. Matplotlib.rc font size. Font size I want 18. The size of the font that I want is 18. After that I want xtick, that is label size I want is in the 16. Similarly in the ytick, xtick I want 16, ytick again I want 16. After that the axis that I want, in which figure we are adding a subplot of 1, 1, 1. This is our basic plotting and drawing we have done using the matplotlib. Now we'll visualize things using UPGMA tree. You already know the full form. Now we have already seen how we are using matplotlib. Now we'll visualize it using UPGMA algorithm, that as I've already told you know the full form of it. For this we are using Phylo, Phylo, Phylo. Remember P with a capital. Phylo.draw. Again, it is a complex process to draw this trees. You don't need to go into its mathematical calculations, and because of this we have already created, I have not created it, but someone already created functions for you that is inside Phylo.draw. The moment you use UPGMA tree and you define axis is equal to axis, that does mean we are just kind of giving it a coordinates. After this we are writing fig.savefig. Savefig is again a particular function that save this particular figure, and the figure is UPGMAT tree. This particular figure is being saved. In this section, the code sets up matplotlib for creating a graphical representation of UPGMA phylogenetic tree. It also adjusts the font size and tick label size for better visualization. Then it draws the UPGMA tree on the figure and saves it as a UPGMA tree and generally .png format. After this, again we have a Python code. You don't have to stop, you have to keep reading. Again the Python code we have, which kind of finds the common ancestors of two clades. Yes, now we are trying to find the common ancestors. For this we'll define a very cute variable named as common ancestor, which is equal to UPGMA tree dot common ancestor, which are from dog, comma, marks, palm, pivot. So we are not trying to read out the common ancestors from them. This part of the code finds the common ancestors of two specified clades within the UPGMA tree. In this case, it finds the common ancestor of dog and marks palm kaiway and stores it in the common ancestor variable. If you go to the next Python code, it basically talks about in very deep way. We are trying to get terminal nodes. What do you understand by terminal nodes? Again, we have to go into very binary trees, things like that, but not going into the depth of the computer involved in this. The terminal nodes for UPGMA, for this we are just defining a variable named as terminals, which is equal to UPGMA tree dot get terminals. Forget what terminal is. You are just trying to get the terminals. What is in the end? What is in the terminal point? What is the end? I just want to grasp that particular point. Here, the code retrieves the terminal nodes, or we in a computer language we call it leaves. It's not the biology leaf, the green one. It's our computer leaf of the UPGMA tree. This tree is again not the biology tree, it's a computer tree. Terminal nodes represent the individual species or sequences in the tree. I hope you understood this. If you want more information on this, you can go and lectures on the binary tree maybe, but you don't need it. Just write it down and you'll see the magic. After this, we'll get the non-terminal nodes. That means the internal. We don't want to now find the end node. We want to find internal nodes of the UPGMA tree, which is non-terminal equals to, we are defining a variable here, non-terminals equals to UPGMA tree dot get underscore non-terminals. Get underscore non-terminals is a function which automatically will give you a non-terminal node. Now this section of the code retrieves the non-terminal node, the internal node of the UPGMA tree. After it retrieves the non-terminal node, the non-terminal nodes represent common ancestors of sequences in, I'll again repeat it for you, the non-terminal nodes represent common ancestors of sequences in the tree. For this, we have a Python code named as, again the next Python code is, we are trying to count the total number of terminal nodes in the UPGMA tree, for which we are again giving a variable name as named as num underscore terminals equals to UPGMA tree dot count terminal. Count terminal is a predefined function. It will automatically count terminals for you. See how easy I have made, people have made life for you to give you by giving you some functions already predefined. This line counts and stores the total number of terminal node leaves in the UPGMA tree. For again, after this we have a Python code that deals with calculation of total branch length of UPGMA tree, in which we will give something from our side, that is a variable which is total branch length, and we'll take something from their side, we'll see that give us total branch length with a function. We'll write total underscore branch underscore length, that will give us length. That's it. Here the code calculates and stores the total branch length of UPGMA tree. The branch length represents the genetic distance along each branch of the tree. The code then proceeds to construct a phylogenetic tree using neighbor joining, call it NJ in our short form algorithm. NJ algorithm you can call it, and visualize the NJ tree and saves it as njtree.png. However, these parts of the code have been commented out in the provided script. So in this complete lecture, we have already seen how using it, how we are using NJTree and all, and I hope the editor does the good work and he or she is showing you the codes along with it. And if you want this code pre-made, if you want this complete code within your hand, you can easily choose. I'll send this particular code in the Python file format. You could just import this all codes into your Jupyter notebook, and all you need to do is just to run them. Also, you need to import some of the files which is related. Suppose if there is a CSV file, you have to import that CSV file. If it is a FASTA file, you have to somehow import the FASTA file in that particular file location. That is the only pain that you have to take. Otherwise, you all need to do is just run the codes. The moment you run the complete code, you could actually see the magic of data visualization that the computer science is giving to the biology and making its mark to make bio future ready. So with this, I'll end today's lecture. Thank you so much, and I'll see you in the next lecture.